In the last video, we derived the update equations for the EM algorithm of the multivariate Gaussian mixture model. Now we want to implement this in Python with the help of TensorFlow. Hi and welcome to this new video. This will be a TensorFlow and TensorFlow probability implementation of the expectation maximization algorithm for the multivariate Gaussian mixture model. For this, we will use the derivations made in the last video that you've also seen in the intro, and we will implement them with detailed explanations and making use of vectorized operations in TensorFlow to improve the computational performance of our code. For this, we will work on some artificial data, but you can easily modify the code to plug in your real-world data and play around with the algorithm to see how it works under the hood. For this, I will also make some remarks towards the end of the video when it comes to certain pitfalls of applying this algorithm to real-world data. Then let's start with importing all the necessary packages. So we need, of course, TensorFlow for the linear algebra. Then we need TensorFlow Probability to query our distributions. I will use it as TFP. We will also use TQDM, which is a really simple progress meter. And let's also visualize the data set with Matplotlib. If you follow this channel, then you know I also have a video on the univariate case where we implemented it in NumPy. So in case some operations here might seem a little bit confusing to you, then also check out this video. So it might help you if you are more familiar with NumPy operations. Then let's create a main function that I will make empty at first so that we can make some switch so that our file is only executed in the Python interpreter. And here I will just call our main function and then we can start filling it out. I said we will perform the algorithm on some artificial data. So artificial, I mean that we create the data from a Gaussian mixture model. For this, of course, we need to define its parameters. So let's define the constants of this Gaussian mixture model. I will use a mixture with two clusters, and there we have the cluster probabilities that are 0.3 and 0.7. We will have the true means given as a matrix. So basically, it's just a list of two vectors, and we have our first cluster centered at 5 and 5. And the other cluster will be centered at -3.0 and -2.0. Then we also have to define our covariances. For this, we will use a list of matrices. So first a list, and here we have our matrix. So in the first row, we will have 1.5. So this will be the variance in X for the first cluster. Then we have a 0.5 is the covariance for the first cluster. And of course, we need it to be symmetric. And here we have a 2.0. And with this, we can then also see whether our EM algorithm correctly recovers the covariances in the covariance matrix. And then for the second cluster, we have a 1.5 variance in X direction again. And here let's use zero covariance so that we can also check how the EM algorithm performs in these kind of situations where we only have a diagonal covariance matrix. And then we also need 0 here, of course, due to the symmetry. And then let's have 1.8 as the variance in Y direction. These parameters will be used to create our Gaussian mixture model. And then we also need to sample it in order to create a data set from which we can then run the EM algorithm. And here we will define n samples to be 1,000. And later on, we can also play around with this a bit. Let me change the name here to covariances, which would be more representative because it's plural here. Matches also the muse here. Okay, then we can define the Gaussian mixture model. But for this, we need the Cholesky factors for all of the covariance matrices. So we have two covariance matrices, so we need two Cholesky factor. And for this, we will use the batched Cholesky factorization of the covariance matrices. Since batched operations are at the heart of TensorFlow probability, this works really intuitively. So let's say we do else true. So L, I mean the Cholesky factor, and S just for the plural. And for this we use tf.linarc.Cholesky, and then we apply it just to the true covariance matrices. And the logic of TensorFlow is that the first axes correspond to batch dimension. So the input dimension of a Cholesky decomposition is of course a matrix, which is a two-dimensional object. And if we feed it with a three-dimensional object, it considers the very first axis as the batched axis. So it actually then performs two Cholesky decomposition, in the best case in parallel, of course. And then we also have two Cholesky factors. So this will be having the same shape as the covariance true multidimensional array. Okay, based on this, then let's create the true Gaussian mixture model. So let me call this the true Gaussian mixture model. And let me add the remark that we want to use for sampling some artificial data. And that's of course the spot in the code that you would replace with your real world data. And for the Gaussian mixture model, we first need a categorical distribution. I will call this cat. And for this we use tfp.distributions.categorical. And the categorical takes a list of probabilities. And here we will use the cluster probabilities. That fully defines our categorical. And then we need normals. And I will also use the plural here because we have to create batched multivariate normal distribution. So we use tfp.distributions.multivariate normal try L for triangular lower, which corresponds to the Cholesky factors that we have here. And this needs first some locations, so the mu's, and we will use mu's true. And since mu is usually a one-dimensional object corresponding to the number of dimensions, and here we have it as a two-dimensional object, therefore TensorFlow probability is automatically recognizing that it is getting a batch normal distribution with a batch shape of 2. So here in this particular case, these are identical, so 2 by 2, but you can also have more mu's or more dimensions depending on your scenario. And then we have our scale trial, and here we will just plug in the Cholesky factors that we created earlier. And I see I should also maybe make this capitalized so that it would be more consistent with what we had before. Okay, let me quickly fix this. Yeah. Okay, then we can create the true Gaussian mixture model. And similar to the intro video, we will use the mixture same family object from TensorFlow Probability, which requires a mixture distribution, which will be our categorical, and a components distribution, which will be our normals. Then we can create a dataset, which would be just sampling this true Gaussian mixture model, and we will sample it according to our n samples that we set earlier. And I will also fix the seed so that this is reproducible. Then let's take a look at the dataset that we have here. And for this, let us run the code. So we run our multivariate Gaussian mixture model. And if everything works, then we should get a printout of the dataset, and that's fine. So the dataset is a two-dimensional tensor with 1000 rows and 2 columns. So it's a really skinny rectangular matrix. And this of course corresponds to the data matrix with 1000 samples, and we are in 2 dimensions. Okay, let's close this down. So let's also plot the dataset. I will use a scatter plot for this. And for this, in order to work, we have to first convert our TensorFlow tensor into the NumPy world. And then we plot the first dimension or the 0th dimension. And then we need the next dimension. And then we also have to let it show the plot. And then running it again, we should get a pop-up. And here we go. And there we see our 2 clusters. The one is centered at -5, -5, and the other one at the other coordinate. And we of course see that the one cluster has no covariance at all, so it's spherical or rotationally symmetric. And here we have some covariance in it. And let's see how our algorithm can recover this. So let me close this down and let me comment out the printing statements, and let me close this down again. And then we can start with implementing the EM algorithm, which we will do as a function. And this EM algorithm takes a data set, it takes the number of clusters it should find in the data, and it takes a number of iterations, because here I won't do a convergence check, so we just let it run for 100 iterations. Let me also make this function empty first to fix the interface, and we will call the EM algorithm on the data set that we just sampled, and we will let it find the same number of clusters that we also use to create the data for. And of course, this could be some sort of a difficulty if you have a real-world data set that you might have to do some grid search over the number of clusters. And this function call will then return class probabilities, and I will call them approx because it's just an approximation. And then we have muse approx, and we have our covariances approximated. Let me just make some pretty printing here. And with this down, let's go back up to the EM algorithm and work on it here. For our EM algorithm, especially for the computational considerations, we needed 3 major axes or 3 major dimensions. So we have the number of clusters, but we also have the number of samples and the number of dimensions. So n samples and n dimensions, which will be important later on when we do the vectorized operations. And we can infer them from the shape of the dataset. That was because, recall, the dataset was this skinny matrix with 1,000 samples by 2 dimensions. I will just call this infer from the dataset. And then for the first time, let me bring over again our summary. And the important point of the EM algorithm was that it was an iterative algorithm, meaning that we make improvements over the iterations. But for any iterative algorithm, we need some initial guesses, which we will draw randomly. So I will put this back aside, and then I will call this draw initial guesses. And we need a guess for the cluster probabilities. And recall, the cluster probabilities is an array of the dimension of n clusters. So in our case, it's 2. And it has the property that it adds up to 1. And for this, we can query the conjugate prior to the categorical distribution, which is a Dirichlet. So we do tfp.distributions.Dirichlet, and the Dirichlet takes an alpha vector that defines how the probability mass is distributed over the simplex. And for this, we will just use a ones array that has the same dimensions as the clusters. And if you watch the video on the Dirichlet distribution, then you know if we put the alpha vector to a 1, this means that we have a uniform prior, so making each of the components in the cluster probabilities equally likely. And then we sample this distribution, and we need to sample it only once. And here I will also fix the seed to 42 so that it is reproducible. Next up, we have to make an initial guess for the mean vectors. And for this, we will use the conjugate prior to the mean vector, which is a multivariate normal, so tfp.distributions. However, I won't use the multivariate normal object because in this case, we can just assume independence over dimensions. So we can just use the univariate normal and just sample it with a corresponding shape. And here I will center it at 0.0 and I will use a scale of 3.0. That is because our means are a little bit off from the center. So this helps us with getting samples that are further away from it. So this could also be a potential tuning parameter of your algorithm. And recall, if we would sample a univariate normal without any sampling shape or batch shape, then this would return just a scalar value. So we will sample this and we will sample it in the shape 2 by 2. And this 2 by 2 is corresponding to the 2 by 2 that we have here. So this would be n clusters and then here n dimensions. And then you also see why we inferred them from the dataset shape. Let me also fix the seed here, and then we're good for the mean vectors. Let's go on to the covariance matrices. And for this, we use the conjugate prior to the covariance matrix, which is the wizard distribution. And for this, we use tfp.distributions.wizard, and we will use the tri-L form, which also takes a triangular lower matrix. Let's set the degrees of freedom to 3 and use a scale tri-L matrix that is just the I matrix, so the identity matrix. So we use tf.I, and then here we need the number of dimensions because this has to match the shape of the covariance matrix, and the covariance is n dims times n dims. So this will just be then the n-dimensional I matrix. And then we have to sample it, and here we have to sample it n cluster times, such that we get an object that's similar to our true covariances, so an tensor with 3 axes basically. So n clusters, and let me also fix the seed here again. And then we of course have our iterative algorithm. Let me represent this with a for loop. So for something in the range of n iteration, and here let me wrap this in the TQDM such that we can get our progress meter. And I will first do a pass here, so let it empty at first. Let's code a return statement that matches our interface so that we return the cluster probabilities, the mu's, and the covariances. And then we can see that this matches what we already wrote down. So if we would now execute the code once again, then we get a printout with all the initial guesses. This is then what we will be using to judge the performance in the end. So we have class probabilities, we have our mu's, and we have 2 covariance matrices. And by chance, the class probabilities are quite close to the class probabilities that we have here. Then we get our mu's tensor, which is off. And of course, the covariance matrices also don't match. So we hope our EM algorithm can find this just based on the dataset. Okay, let's close this down. And then finally, we can start with the heart of the EM algorithm, this iteration here. Let me bring over the results from our derivation. And then we know that we have first the E step and then the M step. And then let's also refer to the numbering that I introduced here. So first step is to calculate the unnormalized responsibilities. So step 1. And how does this work? So the unnormalized responsibilities will be a tensor with 2 axes, the first axis being the number of samples and then the number of clusters. And it is given by multiplying the class probabilities, which is an array of the number of clusters, with the multivariate normal evaluated at the sample points. Okay, so we need the multivariate normal again with our current estimates of the parameters. And in order to do this in TensorFlow Probability, we need again the Cholesky factors of the covariance matrices. So let me again do this here. This is some sort of like a pre-processing step. So we do the batched Cholesky factorization again. So we get our Ls, which are tf.linalg.Cholesky, and then apply this to the covariance matrices. Then we can build our batched normal distribution here with tfp.distributions.multivariate normal trial. And this again takes the locations. And here we take the current estimate of the mean vectors, so mu's, and then scale trial the current estimate of the covariance matrices, or respectively their Cholesky factors. So this will be L's. So then we have in the first point here, go down a bit, we have the unnormalized responsibilities. And let me open a bracket here so that we can put this in the next line. And here we will now use some vectorized operations. So since we know that the responsibilities will be of dimensions samples times clusters, so let me also note this down. Responsibilities is of shape n samples times n clusters. We need to first blow up the cluster probabilities that we have into something which has an auxiliary dimension here. So we do a tf.reshape and reshape our cluster probabilities into a format of 1 times n clusters. So before that, it was just an n clusters array, and now it is an 1 by n clusters array. So we didn't change the total amount of elements in there. This just helps with the batched operations that we do now. And then we element-wise multiply this, and then we element-wise multiply this with our batch normal distribution, evaluate it at the samples. But here we also have to reshape our dataset first. So the multivariate normal is of shape n clusters by n dimensions. Let me also note this down. So the batched multivariate normal is of shape, and here we have n clusters by n dimensions, and our data set is of n samples by n dimensions. So the correct reshaping would be to take our data set and to have it as n samples by 1 by n dimensions. And that is because the convention in TensorFlow probability is the event dimension, so the dimension our multivariate normal is defined over, is always the last axis. And then we have the batch dimension, but not any batch dimension, so somehow the internal batch dimension. And then we can also query it at the same time for multiple samples. So we use the one here as some proxy in order to do a broadcasting of our multivariate normal trial so that it evaluates all the samples with all the clusters and using all the dimensions. So in essence, what it is doing, if we apply this probability to the reshaped dataset, the return shape will be n samples by n clusters. You can also think of it as this three-dimensional tensor, and it's going row-wise. And for each row, it then sees a matrix and evaluates its probability batched on it. So it then returns n clusters. For each of the rows, it turns n clusters, and then we get n samples times n clusters. And if my bracketing is now correct, yes, this should also be fine here. And then if we perform this component-wise multiplication, TensorFlow already does the broadcasting for us, so it will then expand this dimension here, and then our responsibilities is of the correct shape. Okay, with this, we can then do our normalization procedure, which is 0.2. And for this, we have to row normalize. So basically, we ensure that over all the rows in our two-dimensional object, these sum up to 1. So we say that the responsibilities, hope I don't have a typo here, are the unnormalized responsibilities divided by the summation of the unnormalized responsibilities, where we take the summation over the one axis, which is the second axis, which is the axis over the clusters. And we also need to do keep dims equals true, such that the broadcasted division that we are doing here, so the element-wise division, will not raise an error with respect to the shape. And then we have our normalized responsibilities. And then let's also calculate this auxiliary quantity, which is the class responsibilities. So here we have the class responsibilities, and this one will be rather simple. We are just summing over the samples axis, so tf.reduce sum over the responsibilities, and we use the zeroth axis, which is the sample axis, and we don't do keep dims here, so this will then again be just a vector, so a tensor with just one axis. And that's already E step, so let me quickly recap. We first have the unnormalized responsibilities, which we just did in an efficient vectorized fashion. Then we normalized them, and then we had this auxiliary quantity, the class responsibilities. Okay, then let's go to the M step, and the very first stage in the M step is to update our class probabilities, and for this we divide the class responsibilities by the number of samples. So these are class responsibilities divided by the number of samples. That's rather straightforward, and here we also don't have to take care of any reshaping. That is because this is already a one-dimensional or one-axis tensor, and this is just a scalar, so this is already automatically broadcasted, and that's also matching the shape that we've drawn from our initial guesses by the Dirichlet distribution. Then the mean vectors will be a little more difficult. Here we will also use some vectorized operations. Before we do this, let me quickly collect the shape of everything so that it is clear. So we will have the class responsibilities, and this is of shape n clusters. So that's what we've seen here. This will be the 1 over gamma e. And then we have another ingredient, which are just the responsibilities. And this one has the shape n samples times n clusters. Okay, here we go. And then as a last, we have the data set or the data matrix. And here we just had one entry, one row of this data matrix, but we will here consider the entire data matrix. So we have the data set, and this is of shape n samples by n dimensions. Then let us also define the dimensionalities of the mu's. So we have the mu's, and this will be, or has to be, so this is of shape n clusters times n dimensions. And then we see we have all of the three potential axes involved, and the product of this operation has to be n clusters times n dims. Then correspondingly, we have to sum over the samples axis. So the corresponding logic is that summation has to occur over the samples axis, which is of course also what we have here. Okay, so we do mu's is tf dot reduce sum. So this will be our summation here. And now let's blow up the two-dimensional responsibilities into a three-dimensional object, which has n samples times n clusters times n dimensions. And in that sense, responsibilities are a one-dimensional quantity. So we will just use a dummy axis for the very last. So we will do tf.reshape and take the responsibilities and reshape it into n samples times n clusters times 1, so the dummy axis in the very last, and then element-wise multiply it with the dataset, which we also have to reshape. And for this, we of course have n samples, so that these two match. Then by n clusters, we do 1, because the dataset does not belong to any cluster, so because that's the latent information essentially. And here we then have n dims. So what TensorFlow will do for us is a broadcasting over this dimension and also broadcasting over this dimension. And then let's define the axis of summation, which has to be the 0th, because this is the n samples axis, which we want to sum over. And then we have our reduced sum down, and then we will divide by the class responsibilities. But recall the class responsibilities is just a vector. And after the summation, we are left with a matrix, which is n clusters by n dims. So we have to also blow up our class responsibilities. We will do by tf.reshape of the class responsibilities. And we will blow this up into the shape n clusters by 1. And so we have an auxiliary axis over the number of dimensions, so that this is correctly broadcasted in this element-wise division. Okay, then let's continue with the last update, which is for the covariance matrices. And here we already noted it down in this vectorized fashion, so we will translate this one here. But before, let me similarly also collect all the shapes of the involved components. So for the number 3 here, first we look again at the class responsibilities, and this hasn't changed its shape. It's still of the shape n clusters. And let me go down a bit. Then we have x, which is the data set. And this is again of shape n samples times n dimensions. Then we have our mu or mean vector. So mu's, which is of shape n clusters times n dims. And then we also have the responsibilities here. Here in terms of the responsibility vector for one class, but all samples. Here we, however, have it in the matrix version. So responsibilities is of shape, and then here we have n samples times n clusters. Then let's look at our target. So the covariance is of shape and n clusters, because we have n clusters of the covariance matrices. And the covariance matrix is a square matrix, which is symmetric, positive, definite. And this means it is in this last axis n dims times n dims. So we have n clusters times this matrix shape. And if you recall, in the naive implementation, we had a summation. However, here we will use a matrix multiplication, which will just turn out to be more computationally efficient. Okay, so let's go step by step. Let us first do this quantity here, which I will call the centered dataset. And for this, we have to subtract the mean row-wise from the dataset. But we have to take care that the dataset is a two-dimensional object, and the mean vector is also a two-dimensional object. Here it's only a vector because we only considered one mean vector, the Eve mean vector. So let us create the centered data set, which is of shape, or which is a three-dimensional object, which is of shape cluster sample dims. So here we will have n clusters, n samples, n dims. Then if we take our data set, we have to blow it up accordingly. So we do data set, and then since the data set is already samples times dims, we need to add an auxiliary axis in the very first one. So we do 1 and then n samples, n dims. And then we element-wise multiply this with the blown up mu's. So we reshape the mu's, and the mu's were n clusters times n dims. So we add the auxiliary axis in between. So we keep n clusters and then 1 and then n dims. And then we have our centered data set, which also accounts for all the clusters, because of course the mean vector is different for all the clusters. And then we have the centered data set with responsibilities, which is a mouthful, and that's the second quantity here, where we take the centered data set and element-wise multiply it with a blown up responsibilities. So recall the responsibilities are n samples times n clusters, and here we have clusters, samples, dims. And if we were to just do an reshaping, this wouldn't work because here the order is also wrong. We can't just add an auxiliary axis because we also need to swap them. So we will first do a transposition, which is swapping the axis of a two-dimensional tensor in that sense. And then we can add our auxiliary axis. So we take the centered data set as is and element-wise multiply it with something that is reshaped, but first it is transposed. So we transpose the responsibilities, and then we reshape it into, well, it has already the n clusters, so we can use n clusters. It has the n samples. We just have to add the auxiliary axis here such that the shapes match. So then we can make this scalar product basically. So I will call this sample covariances because this is similar to what we did in the maximum likelihood estimate. For this we use tf.matmul, matrix multiplication, and we have first the centered data set, and then we have the centered data set with responsibilities. And then in order to match the pattern here, we have to transpose the first argument. So there is the option to transpose A, which we say true. And the reason we use tf.matmul and not the @ sign, which is also shorthand for matrix multiplication, and that is because we need to do a batched matrix multiplication. So what we do here, let me indicate this, which is a batched matrix multiplication. And recall from the point where we discussed on the application of the normals here, whenever we have an operation which requires TensorFlow to have a certain shape, these shapes are expected to be the last axes. So we have a centered data set, which is n clusters, n samples, and dims, and a centered data set with responsibilities of the same shape. And we want to perform a matrix multiplication in the last two axes. And if we transpose the first one, then these two swap, and we get here something that is then n dims times n dims in the last. But we not only want to do this matrix multiplication once, but we want to do it n clusters times. And that is already accounted for in this matrix multiplication. So indicating the shape once again, here we have n clusters, n dims, n dims. And that's nice. That's already the shape we want to have for our covariances here. Okay, so let me also use the plural, and maybe then it would also be correct to use the plural here, just to be consistent. Okay, centered data sets with responsibilities. Okay, and then some plural here. Yes, okay. Then we need to do the last step, which is dividing by the class responsibilities. Then we get our covariances, and for this we use sample covariances, element-wise division, and then we have our tf.reshape. First the class responsibilities, and this has to be reshaped into n clusters, and then we need 2 dummy axes in order to broadcast over the this matrix axis basically. And then we are done with the update step. However, if we would run this algorithm, then we would actually not be accounting for one thing. So for this, let me go up in our derivation where we had the optimization problem, where we said that we find the update to the arguments by performing the arg maximum, which is essentially what we did here. But then we made a relaxation because a constraint is that all the covariance matrices have to be symmetric positive definite, which we did not account for yet. So we have to ensure this pragmatically in that sense. And the most easy way to do this is to just add some negligible amount to the diagonal of the covariance matrices. So this is the last step. I will call this ensure positive definiteness. So the matrices are symmetric. That is because they are created by the auto product. But then we have to, of course, make them positive definite. And here by adding a small amount to the diagonal. And we will just do this by using a diagonal matrix, scale it with a small value, and then add it to the diagonal. So we say that covariances is the covariances that we have plus, and then the small amount, I will set it to 1e minus 8 and multiply it with tf.I of n dims. However, here we have to also add a batch shape, which is n clusters, such that we not only get one diagonal matrix, but we get n clusters of them. So we add it to all of the covariance matrices. And I see I'm missing an equal sign here. And with this, we are counted for the symmetric positive definiteness. And then we can move this over because our implementation is finished. Okay, then let's see if we did everything correctly. So let's run the algorithm. Maybe you've already spotted the mistake. So then it runs. We should now see the progress bar pretty soon. And we run into some error, which is that the input matrix is not invertible. In general, that's an error that could appear also when the code was working correct. I will leave some words on that later. But here is actually that we have two problems in the code. So first we have a multiplication instead of a subtraction here. So because of course, if we center the dataset, we have to subtract the mu's, not multiply with them. And I also wrongly called it the class probabilities and not the cluster probabilities, which is also a common name for them here. But if we run it now, then we should actually be fine. And let's see, okay, so it runs. I also printed a data set while debugging. We can also fix this real quick. And here we go, perfect. So let me quickly disable the printing of the data set. And then let's compare the found values with the true ones. Let me make it a little bigger here. And let's check first the cluster probabilities. We have one with 0.684 and one with 0.315. That's getting quite close. Here we also see that the order is swapped, so it does not necessarily have to be in the same order as the cluster probabilities. For the mu's, we are getting also quite close, I would argue, just from the I norm here. And the covariance matrices also seem to be fine. And interestingly, we are getting close to finding that one of the covariance matrices is actually a diagonal one and the other one has some covariances, so some off-diagonal elements. Of course, we're getting better the more samples we have. So let's increase this to 10,000. So if we then run our algorithm, so then we see our progress bar again, and you see it's already getting a little bit slower, but actually for the fact that we are crunching 10,000 samples, it's still quite fast. And then we see, well, our approximations have gotten better. We are getting closer to the true values. And we can even go a little higher and do 50,000 samples. And let it run here. Then let's see if we are getting closer to this 0.0 in the second covariance. So you also see that slowing us down, but due to the fact that we use the vectorized operations, we're having a good computational performance here, I would argue. And that's quite a good result. So we see that we are really close to the values that we started with. So let me reduce this again to 1,000. because I want to leave some remarks on some other points. So as said, we already had the problem that our covariance matrix is not positive definite, or in other words, it said it was not invertible, but that means that the Heuristic factorization that we have to do in every iteration, so basically here, is not working. And that can be caused by a lot of things. Usually a big influence on the performance are the initial guesses here. So these one. So it might be reasonable to choose them, that you outfit them with the prior knowledge that you hopefully have on where you would expect the clusters to be, or the parameters of the cluster. Also feel free to download the code from the GitHub. You find a link in the video description, and play around with the seed, how this influences it. Maybe having a different seed for the initial guesses and for the artificial data that we create here. And something that we already considered in the univariate case is that our optimization problem is non-convex, which means that there are multiple local optima. So basically those points our algorithm will converge to, and we are unsure if we are really in a global optimum. So graphically speaking, if we were to scatter plot our data, and it's even just visually hard to distinguish two clusters, then this is also hard for the algorithm. So there are multiple configurations where one could do the clustering. So you might also consider sieving or other meta algorithms. As said, we did a video on this in the univariate Gaussian mixture model. And many other pitfalls that can occur here. Also feel free to write a comment and speak about your experiences with using the EM algorithm for the multivariate Gaussian mixture model. That's now the end of the video. If there are any questions left, please write a comment. I would be happy to help you. If you enjoyed the video, then also consider liking and subscribing. Here you will now see similar videos, and I hope to see you next time.